This is Darrell with Hands-On Cisco Training, Episode 15, Introduction to OSPF. Today we're going to talk about a more popular routing protocol, the Open Shortest Path First protocol. Last episode we talked about the shortest path algorithm, where if every router knew what every other router was connected to in terms of networks and routers, then each router could figure out the best way to get to the destination. The problem is that the shortest path first algorithm requires that all routers know every network that every other router is connected to. The goal of OSPF is to distribute that information to all routers. Each router will tell every other router what it's connected to, and then every router has what it needs to execute the shortest path first algorithm. OSPF distributes that information in link state advertisements, which are just packets with the routing information. There are several different types of link state advertisements. We'll start with router LSAs, which are type 1, and network LSAs, which are type 2. OSPF routers must become neighbors to exchange link state advertisements. Let's look at our map for today. We have our same three routers, top, middle, and bottom. I've added a new device. It's actually a Cisco 3524XL switch. However, I'm not doing anything complicated on the switch today. I just have all of the ports on VLAN 1, which is the default configuration, and I have the three Ethernet interfaces of my three routers connected into it. So I have a total of 7 subnets today. 3 on my serial links, 1 on my Ethernet links, and then 3 loopback interfaces. So the top router, for example, has loopback interface 0, interface serial 0, interface serial 1, and interface Ethernet 0. Let's look at its config. So interface loopback 0, IP address 172.16.1.1/24. Interface Ethernet 0, IP address 172.16.7.1/24. Interface serial 0, IP address 172.16.2.1/24. And interface serial 1, IP address 172.16.6.1/24. That's a DCE interface, so I set a clock rate of 64,000 bits per second. And that's it. The rest of the config is default. One interesting side note, apparently the default config on this old version of iOS has the web server enabled, which is a security problem. Newer versions of iOS have the web server disabled. That's something that you want to watch out for if you're in production. You don't want people logging into your routers over the web and trying to manage them for you. Okay, the first thing that we want to do is let's look at our CDP neighbors. So we have one neighbor out, the bottom router is out our serial 1 interface, and it's a Cisco 2511, and it's connected to its serial 0 interface. The left router is out our serial 0 interface, it's a 2500, and we're connected to its serial 1 interface. And I have a switch which is with the default configuration, so it thinks its host name is switch. It's out my Ethernet 0 interface, and it's a 3524XL. If I do a show IP OSPF interface, I see that no interfaces are enabled for OSPF because I have not configured the routing protocol yet. If I do a show IP route, I have 4 routes, which are my 4 directly connected subnets. Again, the C over here means directly connected. Let's turn on a routing protocol. Conft router OSPF, and then we need a process ID. So router OSPF 1. You can have multiple OSPF processes on a router, and each would work independently. The process ID is not included in the OSPF advertisement. That's why it's called a process ID. If it was included in the advertisement and had significance outside the router, then we'd tend to call that an autonomous system number. So the EIGRP protocol includes that number in the advertisements. So if you do router EIGRP 1, it would be considered autonomous system 1. This is OSPF. We just do router OSPF 1. That's a process ID. Now to turn on our interface, turn on a routing protocol on an interface, we need a network statement. So network 172.16.2.1, so it's network, although that would have worked without the K because of command line completion. 172.16.2.1, let me hit a question mark. Now it needs wildcard bits. What the network statement does is it turns on the routing protocol on the interface if the IP address of the interface matches the IP address specified in the network statement. So on serial 0, our IP address is 172.16.2.1 and it's a /24. As an example, let me give a network statement that corresponds to a /24. Now we're dealing with wildcard bits or don't care bits. What bits don't we care about? Well, we do care about the first octet, so that's a 0. We do care about the second octet, so that's a 0. We do care about the third octet, so that's a 0. This is a /24. We don't care what the last octet is. It's all inside the /24. So our last bit of don't care bits is 255. And that was an incomplete command. I hit the up arrow, question mark, area. OSPF has a concept of an area. Each area executes the shortest path first algorithm. The shortest path first algorithm can get overly complex if you have too large of an area. So that's why they allow you in OSPF to have multiple areas. We will talk about multiple area OSPF in a later episode. For now, we just want to make everything area 0, which is also known as the backbone area. Area 0. So that means that any interfaces with IP addresses that start with 172.16.2. anything, because of the don't care bits of 255, will be in area 0. So let's do a show run, type begin router OSPF. And you can see that I typed in network 172.16.2.1, 0.0.0.255, but the router put in my config network 172.16.2.0 with don't care bits of 0.0.0.255. The reason is because we don't care what that last octet is, because our don't care bits are not 255. So it doesn't matter whether it's a 1 or a 0. And so the router, for consistency's sake, gets rid of any bits, changes any bits that were non-0 to 0 when you're in the don't care bit area. Let's look at show IP OSPF interface. As you can see, I now have one OSPF interface, which is the serial 0 interface. And up here at the top, you can see my network statement is 172.16.2.0, 0.0.0.255. And the IP address on this interface is 172.16.2.1. 172.16.2.1 is inside this range with these don't care bits. So that means that this interface will have OSPF turned on and it will be assigned to area 0. And you can see it's correct. It's our one interface, which is in that range, is an OSPF interface. It is in area 0. The area 0, it's process ID 1 because it's router OSPF 1. The router ID is an identifier that is unique for every router, and by default it uses the IP address of the loopback interface. if you have multiple loopback interfaces with multiple IP addresses, it chooses either the highest IP address or the lowest IP address. I can't remember offhand. So even though OSPF is not enabled on loopback 0, which is 172.16.1.1, that is still the OSPF router identifier for this router. And that router identifier is included in every advertisement. And so one important message there is that you'd better have unique loopback addresses on all of your routers, or the OSPF routing process will get confused because it will think that the two routers are the same if they have the same loopback address. Okay. The network type is point-to-point. OSPF has multiple network types, and we'll run into multiple examples. The reason this is point-to-point is it is a serial interface which can only have two endpoints on it. It's not like Ethernet where you can plug multiple ports into an Ethernet hub or switch. In fact, that's exactly why I plugged in this switch with three interfaces, so we can see an example of a different type of interface. But for now, this is a point-to-point interface. Now we have the default timers, hello timers. So every 10 seconds, our OSPF process will send a hello message to the other side. If it does not, the dead timer is 40 seconds. So if it does not receive a hello within 40 seconds of, if it does not receive a hello within 40 seconds, which is 4 times the hello time, it will assume the other side is dead. And also has a wait time of 40 and a retransmit time of 5. I'll talk about those later. It said a hello was due in 1 second, so when I executed this command, it must have been 9 seconds since the last time it sent a hello message. Neighbor count is 0. What that means is I have not seen any OSPF neighbors out this interface. Now there's another router out this interface, the middle router is out this interface, but I have not turned on OSPF on that router. So a neighbor is when two OSPF routers see each other and agree with their configuration to become neighbors. But at this point, this is the only router and the only interface that we have OSPF turned on. Okay? And that's it for that. Let me turn on OSPF on another interface. Conf T, router OSPF1, network 172.16.6.1, and then question mark, we want our don't care bits. I'm going to go with 0.0.0.0 and area 0. Now this is different. My interface is 172.16.6.1, and it's a /24, so you might think that I need to have don't care bits of 0.0.0.255 to match the /24. But that's not what the network statement means. You don't need the network statement to match the network subnet. All the network statement means is if you have an IP address on an interface that matches the network statement, then you turn on OSPF on that interface. So 170.16.6.1 is the IP address of that interface, and I care about every bit, but it's still going to match. So I will execute that command. Show run type begin router OSPF. And this time you can see that the network command was put in exactly as I put it. Let's see if we turned on OSPF on the second interface. Show IP OSPF interface. And you can see I now have two interfaces, including my new one. Serial 1 is up, line protocol is up. Internet address 172.16.6.1. It's assigned to area 0. It's part of OSPF process ID 1. My router ID is still a loopback. The network type is point-to-point. The cost is 64. A 100 megabit interface, which would like a 100 megabit Ethernet interface, has a cost of 1 by default. This is a serial interface, My bandwidth is a serial interface has a bandwidth. Let's look at it. Show int serial 1. This is show interface serial 1, and it thinks that the bandwidth is 1.5 megabits. Well, 100 megabits divided by 1.5 megabits is approximately 64, which means that show IP OSPF int, that is where the cost of 64 comes from. It is 100 megabits divided by the bandwidth of the interface, which is the default. You can adjust that. State, it's a point to point. We've got our default timers again. At the time I executed the command, the next hello was due in 4 seconds, meaning we were going to send hello in 4 seconds. And that is it. Okay, so we've got OSPF running on some interfaces. Let's look at our routing table. Oops, that's not a routing table. Show IP route. There's our routing table. I don't have anything OSPF in my routing table. That's interesting. But that makes sense because all of my networks are directly connected. And a directly connected network is more believable. Keep in mind the whole point of a routing protocol is for routers to communicate routing information to each other. Routers already know all the interfaces that they're directly connected to. What the top router knows that it's directly connected to these 4 subnets. But the top router does not know what the middle router is connected to. OSPF is a way for the top router and the middle router to communicate to tell each other what they're all connected to. But I have not configured OSPF in the middle router, so of course the top router does not have any information from the middle router yet. But let's see what information it does have. Show IP OSPF database. Remember I was talking about link state advertisements. The whole point of OSPF is to exchange routing information throughout the area, to send all of your information, all the networks that you're connected to every router in the area, and it does that via link state advertisements. The first type of link state advertisement is the router link state advertisement. Every router generates a link state advertisement for itself, and the link state advertisement has the identifying router, which is the loopback address on the router, 172.16.1.1, and it has a lot of information in the link state advertisement. Show IP OSPF database is just a summary of the whole database. Now this link state advertisement is 189 seconds old, which is approximately when I configured the second network statement, which means that the second network came up in OSPF. Let's do a show IP OSPF database ? And I can ask for many different things about the OSPF database. Like I can ask about the different types of LSAs. 2 types of link state advertisements we know about. One is router and one is network. Router is type 1, network is type 2. Now we don't have any network LSAs in our database yet. We have a router LSA, which is our own LSA. Router ? Show IP OSPF database router, and I can hit I can hit carriage return right now, or I can hit self originate, or I can hit the link state ID, which is the loopback address of the router. So let's try just a return, and it gives me the detailed information for all of the router LSAs. So here we have one router LSA, which is the from router with the unique identifier 172.16.1.1. Again, that is our loopback interface, and it's process ID 1, and the link state is now 306 seconds old. The options no type of service capability, which is a QoS thing, which was never. The link state type is a router LSA. The link state ID is our loopback address. The advertising router is our loopback address. The link state sequence number starts at 880,000,002. It 80,000,001 is the first one, and then 80,000,002 is the second one, and it will go up from there until it reaches the max int, and then it will start over at the bottom. It has a checksum. It has a length. The LSA is a length, I believe that's 48 bytes in size. It has two links. As you know, we turned on OSPF on two interfaces. And the first link is connected to a stub network, meaning that there's no other neighbors on that network. And the network is 172.16.6.0/24. And the metric is 64, which is the cost. Again, the metric is 100 megabits divided by the bandwidth, which is 1.5 megabits. So, and then here's the second link in the LSA. It's also connected to a stub network because we have no neighbors out that interface, and it is 172.16.2.0, and it's a /24, and the metric is also 64. So you can see this LSA, this router LSA, identifies every subnet that the top router is connected to. At least every subnet that we're connected to that OSPF is enabled on. Now, OSPF is not enabled on the Loopback interface, so let's go ahead and do that. conft router OSPF1 network 172.16.1.1, which is an exact match for the IP address on the interface. Don't care bits of, actually I'm going to go ahead and 1.0, I'm going to go ahead and do the don't care bits of 0.0.0.127, which doesn't make any sense at all. The IP address is 172.16.1.1. The subnet is a /24. Oh, yeah, 0. But the point is that 172.16.1.1 does match 172.16.1.0 with don't care bits of 0.0.0.127. Show IP OSPF int. And my OSPF interface, I have a Loopback 0 interface, and its up, line protocol is up. It's 172.16.1.1/24. It's area 0. It's a different network type. It's network type Loopback, and it has a cost of 1. Why does it have a cost of 1? Well, Loopback interface is treated as a stub host, which is interesting. Even though the subnet is a /24, we'll see later in the routing advertisement, OSPF treats it as a /32. Our cost is 1. Let's do show int LO0. What is the bandwidth of a Loopback interface? The bandwidth of a Loopback interface is, looks like kilobits, megabits, looks like 8 gigabits is the bandwidth of a Loopback interface, which is greater than 8 gigabits is greater than 100 megabits, right? So the cost is 100 megabits divided by the bandwidth, which is 8 megabits, so that cost is well below 1, but you can't have a cost below 1, so it just assigns it a cost of 1. Okay, so because 1 is the smallest cost you can have other than 0, because cost is an integer. Show IP OSPF interface. It's IP address, area 0. We got the router ID is the Loopback. Network type is Loopback. Cost is 1. It's treated as a stub host. That's everything for the OSPF interface for that. It's a lot shorter than Serial 1 because Serial 1 talks about all of the advertisements, the hello advertisements and the neighbors and such, which on a Loopback, it doesn't go anywhere. You can't have neighbors, so you don't do any hellos or anything. Okay, let's look at our database again. Show IP OSPF database. We still only have one link state advertisement in our database, and it is a it is still a router LSA. Let's look at it. Show IP OSPF database router, and you can see our OSPF database. Link state advertisement age is 165 seconds since I made that config change. It's a router type LSA. The link state ID is our loopback still. The advertising router ID is our loopback. Notice the sequence number. It used to be 80,000,002, now it's 80,000,003. When the router configuration changed, I generated a new links router LSA, and when I did that, I increased the sequence number by 1. That way, all of the other routers in the area, not that there are any yet, but all the other routers in the area knew that this LSA was more recent than the previous LSA, and so they threw out the previous LSA and they're listening to this one. We have a new checksum. The length used to be like 48, now it's 60 octets. There are 3 links, and stub network 172.16.1.1. This is our loopback, and even though the loopback is configured as a /24, it is advertised in OSPF as a /32, which is just the way it is. And then my other 2 stub networks. Okay, I have a 4th subnet that I want to create or activate. Subnet already exists, but I want to activate it in my OSPF. So router conft router. Well, let me show you something. Show run type begin router OSPF. Let's say that this is a critical router and it's a critical network. And I think I have redundancy because I have 3 links back to the rest of the world. And here's my configuration. And the problem is my configuration, I've made an error. I have not enabled my routing protocol in one of my interfaces. And so even though it might be able to ping across it, I'm never going to send any traffic across it, because at least not to multiple hops away, because the routing protocols are just ignoring it. That's a mistake. Having a separate network statement for every interface is error prone. One way to improve the reliability of your network is to minimize the number of configuration errors you make. And one way to minimize the number of configuration errors is to simplify and standardize your configuration. So if you want all of your interfaces on a router to be in area 0, the easiest way to do it, conft router OSPF1 network 0.0.0.0, and let's not care about any bits, 255, 255, 255, 255, area 0. Show run pipe begin router OSPF. So any IP address on our router is going to match this network statement because we don't care about any of the bits. And that means these other 3 lines are unnecessary. And if we bring up a 5th interface someday and configure an IP address on it, it's going to be immediately available in OSPF. So we're far less likely to make an error and fail to put our interface into OSPF. That's good news. The bad news is that any interface we configure will go into our routing protocol, even if we might not be ready for it to do so. So that's a decision to make, whether you want to manually add interfaces to OSPF one at a time with network statements, or whether you want to just do it for the whole router all at once. And I personally generally do it for the whole router all at once, because usually when I'm bringing up an interface, I'm testing it anyway. And so I can deal with that then. But if I fail to enable routing on an interface, then a year later, one of 2 links to a building might go down, and the second link to the building would not take over the traffic because sometime a year ago somebody forgot to configure a network statement. That means the whole building's down, and that usually means that management, that hundreds of customers in that building are affected, and management wants a post-mortem and all that bad stuff. Okay, so network 0.0.0.0, 255.255.255, area 0 means that OSPF will be enabled on all interfaces no matter what, which eliminates one possible cause of human error causing an outage. Okay, show IP OSPF int. Scrolling back, we now have 4 interfaces that have OSPF enabled, and here's Ethernet 0, line protocol is up, the internet address is 172.16.7.1/24, it's in area 0. The process ID of the OSPF process is 1. The router ID is the loopback. Network type is broadcast. Ethernet is a broadcast network, meaning that you can have multiple routers, 3, 4, 5, 6, 7, connected to that Ethernet network. In fact, here we have 3 routers that we're going to connect to this, that are connected to this network. Designated router is 170.16.1.1. That's me, and that's my loopback address. The designated router, one of the problems with OSPF is that if you have 20 or 30 routers connected to an Ethernet net and they all become neighbors with everybody, well, let's say if you have 10 routers, each neighbor with the 9 other routers, that's what, 10 times 11 divided by 2, that's 55 neighbors. That's a lot of processing power. What happens in this type of network is that you elect a designated router and a backup designated router, and all of the routers become neighbors with the designated router and the backup designated router, and that's it. And that way, instead, if you had 10 routers, instead of 55 neighbor relationships, you would have 9 neighbor relationships for the first one, plus 8 neighbor relationships for the second one, so you have a total of 17 neighbor relationships, which is not bad when you have 10 routers. Okay, but it's a new network type broadcast with different rules, including a designated router. There's a designated router priority, which 1 is default. There's no backup designated router because I only have 1 router on this network with OSPF configured. Let's look at our OSPF database. Show IP OSPF database. And I have a router link state. Let's go and I'm not seeing any network link states yet, which is interesting, but show IP OSPF data router. Okay. Here's my router link state. Notice the sequence number has incremented again. Now it's 80,000,004. I got a new checksum. My length is a little bit larger. I've got 4 networks. They're all considered stub networks because I don't have any OSPF neighbors on any of them. And that's actually, here's the new one, 172.16.6.0/24, which is the new Ethernet subnet. Actually, I'm sorry, the Ethernet subnet was 172.16.7.0/24, and the metric on this one was 10 because it's a 10 megabit Ethernet connection. The default metric, 100 megabit, is a cost of 1. 100 megabit divided by 10 megabit is 10, so the cost of this network is 10. Okay, that's it on this router. I've got all my interfaces configured. I do show IP route, and I don't have any OSPF routes yet because I don't have any other routers to talk to. So let me plug into the console in the middle router and fix that. I'm going to change the host name to middle because that's what my diagram says. That's one of the other things. If your documentation does not match reality, maybe you should think about correcting reality to match the documentation, because the documentation is the way you meant it to be, right? Okay, sorry, just a different way of thinking about things. Okay, conft router. Okay, I already conft router OSPF 2. It's a process ID. It has no significance outside the router. Network 0.0.0.0 area 255.255.255 to don't care bits, area 0. And that was it. I just configured OSPF in this router. Router OSPF 2, and then I just assigned all of my interfaces to area 0. And then look at these log messages. OSPF process 2. OSPF, the severity of the message is 5, which I think is, I can't remember what level that is. the lower the number, like 1 is like a critical emergency alert, and 7 is debug, and 6 is informational, and 5, I can't remember what 5 is, might be like a warning or something. We have process ID 2, and I have a new neighbor, which is 172.16.1.1, which is the loopback IP of, so here's the middle router, and I've got 2 interfaces which can communicate with the top router, which is 172.16.1.1. One is serial 1, and one is Ethernet 0. And guess what? I formed neighbor relationships on both of them, and I went from loading to full, and then loading done, meaning that we exchanged our routing information. Show IP OSPF interface. Let's look through my interfaces that are OSPF enabled. Serial 1 and process ID 2. Network type is point-to-point because that's a serial link. Cost is 64. And let's see, hello do in 1 second. And neighbor count is 1. I have 1 neighbor out serial 1, which makes sense. Here's my serial 1, and here's my neighbor. Neighbor count is 1. Adjacent neighbor count is 1. I am adjacent with neighbors, whose name identification is 172.16.1.1. Note, the IP address of the neighbor out this interface is 172.16.2.1. But as far as I'm concerned, his name is 172.16.1.1. This is his identity. And I'm adjacent with that one. And then serial 0 is up. It's a type point-to-point. There are no neighbors on that one. That's because serial 0 goes over to the bottom router where I have not configured OSPF yet. Loopback 0 is up. And then here's the Ethernet 1 is up, line protocol is up. I've got my IP address, my process ID, it's type broadcast. My state is backup designated router. Remember, the top router was the designated router on that net because he went up first, and he had a priority of 1. And OSPF went up on my router second, and I also have an OSPF priority, designated router priority of 1. But whenever you have a router that is already the designated router, it stays the designated router, so I became the backup designated router. And backup designated, so the designated router is 172.16.1.1, which is the top router. The backup designated router is me, 172.16.3.1, which is my identity, which is the loopback address. Neighbor count is 1, adjacent neighbor count is 1, and I'm adjacent with the neighbor, sort of repetitive here. Okay, that's it for show IP OSPF interface. Let's look at show IP OSPF database. This is interesting. I now have 2 router link state advertisements, which makes sense because I have 2 routers running OSPF. One is from the top router and one is from the middle router. But I've also got a network link state. The network link state is for 172.16.7.1, which is this subnet on the switch. It's the broadcast network, and it comes from the designated router, which is 172.16.1.1. So what happened is on the Ethernet network, where the top router is the designated router and the middle router is the backup designated router, the designated router has the job of originating a link state advertisement for that subnet, which is a network type LSA. So we now have 3 LSAs in our environment. 2 for the 2 routers, plus 1 for the shared Ethernet network, which is of a type broadcast. Remember back in the show IP OSPF interface, the Ethernet network is network type broadcast. And one characteristic of broadcast nets is that If you have multiple routers in the broadcast net, a designated router is elected, and it will originate a OSPF. OSPF database, and a network LSA for that. Let's go take a look. Show IP OSPF database router 172.16.1.1. This is the router LSA that we've been looking at from the other router, the top router, this whole time. Let's look at it again and see how it's changed. Okay, its age is now 348 seconds. The link state ID and the advertising router are still 172.16.1.1. The sequence number is now incremented to 80,000,006. It's got a new checksum. It is yet again longer. It now has 5 links. It is connected to a transit network where it has a designated router address of 172.16.7.1. That's the IP address of the designated router on that subnet. And then it has the stub network, which is 172.16.1.1, which is its serial 1 interface. And that's a point-to-point going to another router, but that other router doesn't run OSPF, which is why it's a stub. And it has another stub network, 172.16.6.0, which... 172.16.1.1, this is the loopback. This is the loopback, which is, of course, a stub. And this is that serial 1 interface, which goes to the other router not running OSPF, which is why it runs a stub. And then it has a link connected to another router, which is a point-to-point, which is 172.16.3. This link is a point-to-point link, and the subnet is 172.16.2.1/24, but the router on the other side is identified as 172.16.3.1/24. So it identifies that the router on the top is connected to another router, and it's connected to the stub network, which is that subnet. So that's interesting. It thinks it has 5 links, even though it has 1, 2, 3, 4 links. The reason it thinks it has 5 is because it thinks it's connected to this loopback, it thinks it's connected to this serial 1, it thinks it's connected to this Ethernet broadcast network, it thinks it's connected to this subnet, and it's telling you that it's connected to this router via this subnet, via a point-to-point link. So it's like this point-to-point link counts twice. But you note, it did not say, the top router did not say it was connected to this router via the network subnet, it just said it was connected to the network. And the reason is, show IP OSPF database, the top router is saying it is connected to this network, and the designated router for this network, which is also the top router, originates a network LSA, which says what routers is the network connected to. Let's look at that network LSA. This will be the first time we look at a network LSA. Show IP OSPF database, hit question mark, and you can see the option we've been using so far is router, but here's network, which is another type of LSA. Show IP OSPF database network, and I'll hit return, and it shows me all my network LSAs, which I have 1. So the network link states its age is now 556 seconds. It is a network LSA. I have the designated router is 172.16.7.1. I'm sorry, that's the link state ID of the designated router. I have the advertising router, which is 172.16.1.1. I have a sequence number, which is 80,000,001. Remember, this is a new LSA. It's different than the router LSA above, so it started counting at 80,000,001. It has a checksum. It has a network mask, and it says 2 routers are connected to the network. So this is how the LSAs are saying, hey, this router is connected to this network, or this point, this stub network, and this network, and this network, and this network. And this router, we have another router LSA saying it's connected to this network, and this network, and this network, and this network. And the network here has its own LSA, a network LSA. So we have complete routing information because we've exchanged these link state advertisements. In fact, show IP OSPF database. I have 3 LSAs. One is sequence number 80,000,006, one is sequence number 80,000,003, and one is sequence number 80,000,001. Let's go to the top router. Here I am on the top router, show IP OSPF database. And again, I have 3 LSAs. One with sequence number 80,000,006, one with sequence number 80,000,003, one with sequence number 80,000,001. My OSPF databases are completely identical on both routers. Both routers have the same 3 LSAs with the same 3 sequence numbers, so they have the same information, and they can both execute the shortest path first algorithm and get the same answers about the optimal path to get from point A to point B in the network. And so they execute the shortest path first algorithm, and the result is the routing table. And you can see that here's the routing table, and let's see, I still have my 1, 2, 3, 4 connected routes. However, I've learned 2 new routes via OSPF. I've learned the route to the loopback on the middle router, which is the loopback is 170.16.3.1/24, but in OSPF, remember, it got advertised as a stub route, and it got advertised as all loopbacks get advertised as a /32 in OSPF. And then on the other route is 170.16.4.0/24, which is the middle router's other serial interface. Now here's the cost. Look at the cost. The best way to get from the top router to the middle router is via this Ethernet network, which is 10 megabits. A 10 megabit network has a cost of 10 because 100 megabits divided by 10 megabits is 10. And then the loopback interface has a cost of 1. So you can see the cost to get to this loopback interface is 11. 10 plus 1 is 11. This is the cost. This number here, 110, is the administrative distance. That is how believable the route is. OSPF has a default administrative distance of 110. Now, if you remember, RIP has an administrative distance of 120. OSPF is a superior routing protocol to RIP in many aspects, and as a result, Cisco has decided that it should have a lower administrative distance. Lower wins. A directly connected route would have an administrative distance of 0. A static route has an administrative distance of 1. So connected routes win over static routes. Static routes win over OSPF. OSPF wins over RIP. However, I'd also mention more specific always wins. A /32 is always better than a /24. A /24 is always better than a /22. A /22 is always better than a /16. So when you're deciding which route to follow for a particular IP address, you look through your routing table for all routes which match that IP address. You pick the most specific route in terms of subnet mask. If you have 2 routes with the same subnet mask to a particular destination, then you pick one with the lowest administrative distance. And if you have 2 routes which both go to the destination, have the same subnet mask, have the same administrative distance, then you choose the one with the lower metric. The other OSPF route going to that other router is the one for its serial interface, So let's remember the cost to get from the top router to the middle router through the 10 megabit Ethernet network is 10, and then the cost of the serial interface is 64, so that cost should be 74 total, and you can see the cost to get to that subnet is indeed 74. Okay, let's go ahead and look back at our config. Here's our OSPF configuration. Router OSPF 1, the log adjacency changes means that if you get a new OSPF neighbor or you lose an OSPF neighbor, it prints it out in the log. That's useful to have. It turned out that was default here. And then I have 4 network statements, but this is the only one I needed. So really, all I needed to do is router OSPF 1, network 0000, 255, 255, 255, 255, area 0. And that's all I needed to do to configure OSPF on all my interfaces with every interface in area 0, and then I was done. Everything else today was just talk about how it works and why it works, but the configuration for a small network is simple. You just turn on OSPF on all your interfaces in area 0. And that concludes today's talk about an introduction to OSPF. There's lots more to talk about, and we will talk about that in a future episode. Thank you.